After studying this module, you shall be able to classify the two systems for nitrogen fixation, identify the transition metals that are capable to form the stable complexes with the molecular nitrogen, know the mechanism for in vivo nitrogen fixation and its importance and limitations, analyze the structure and composition of proteins incorporated in the complex enzyme called nitrogenase. Learn the mechanism of action by nitrogenase in the nitrogen fixation. Identify the role of ATP hydrolysis, know the binding site for nitrogen fixation and learn the sensitivity of nitrogenase. Introduction. Nitrogen fixation represents one facet of the nitrogen cycle that involves the global interconversion of nitrogen between different oxidation states. Nitrogen fixation is essential to sustain life through the continual replenishment of metabolically usual forms of nitrogen. The catalytic efficiency of biological nitrogen fixation, which proceeds under ambient conditions, stands in pronounced contrast to the Haber-Bosch process and other synthetic systems that require high temperature to get reasonable conversion rates. Therefore, the molecular mechanism of biological nitrogen fixation has been a topic of great interest to understand the origin of its catalytic efficiency. Bioinorganic chemistry behind nitrogen fixation can be explained via two different systems: in vitro nitrogen fixation and in vivo nitrogen fixation. In vitro nitrogen fixation, in 1965, Alan Antonov prepared an isolated ruthenium complex cation by the action of hydrazine hydrate on various compounds of tri- and tetra-positive ruthenium. Example, ruthenium trichloride. This discovery that molecular nitrogen was capable of forming stable complexes with transition metals led to the extensive investigation of the possibility of nitrogen fixation via such complexes. Of the various systems investigated, the one employing titanium-2 was the first to be successful. Titanium-2 alkoxides form dinitrogen complexes which may then be reduced with subsequent release of ammonia or hydrazine. Although this kind of process is not commercially competitive with the Haber-Bosch process for the synthesis of ammonia, but still shows promising results in the synthesis of other nitrogen compounds such as hydrazine and other organic nitrogen compounds. Mechanism of in vivo nitrogen fixation. For the conversion of dinitrogen complexes into ammonia, powerful reducing agents were required since they are as unreactive as atmospheric nitrogen. Later, an important development was the discovery where certain phosphine complexes of molybdenum and tungsten containing dinitrogen yielded ammonia in the presence of an acidic media. Reaction occurs when the compounds of this type with metal molybdenum or tungsten could be alkyl or aryl are treated at room temperature with sulfuric acid in methanol solution, where THF is tetrahydrofuran and DPPE is 1,2-bis diphenyl phosphinoethene. Both the above reaction take place at room temperature and atmospheric pressure. The reducing agent is Grignard reagent. At molybdenum and tungsten centers of this type, the bound nitrogen can be reduced by protons at the terminal nitrogen with electrons supplied by the metal to give the cycle of reduction. This has been represented in figure. This reaction sequence is important as it models the in vivo nitrogenase system that employs molybdenum. Figure represents the cycle of reduction. Studies of the reaction intermediates support the proposed model. The partly reduced nitrogen species shown in the cycle have been isolated when bound to a metal. Example, a recently obtained example of an ammonium ligand is the X-ray structure of tungsten chloride complex. If the system is quenched early in its reduction cycle, the intermediate produces hydrazine. It seems reasonable to propose this type of reduction cycle for nitrogenase. Importance of in vitro nitrogen fixation. It provides a model for in vivo nitrogenase system that appear to employ molybdenum. It provides insights into the development of useful catalysts for the industrial fixation of nitrogen. Whereas the limitations of in vivo nitrogen fixation is it is not a continuous process, that is, cycle stops after one turn giving 2 ammonia molecules per metal complex. Reaction stop when metal gets completely oxidized, since metal is the only source of electrons, and to restart, more electrons must be supplied from the electron transfer system. In vivo nitrogen fixation. In vivo, nitrogen fixation occurs within certain symbiotic or free-living bacteria to fix nitrogen into useful compounds. The enzyme system responsible for fixing nitrogen is known as nitrogenase. Nitrogenases are a family of metalloenzymes that can catalyze a key step in the global nitrogen cycle. It plays a critical role of fixing gaseous nitrogen and makes nitrogen compounds available for plants. It is distributed in a group of symbiotic bacteria and also in non-symbiotic or asymbiotic bacteria. Of all, the most important nitrogen fixing species are the mutualistic species of Rhizobium residing in the root nodules of leguminous species. Nitrogenase. Structure and composition of nitrogenase. Long and intensive studies have revealed that nitrogenase is a complex enzyme comprised of two metal containing proteins, neither of which exhibit any physiologically relevant activity in the absence of the other. These are usually called as the iron protein and molybdenum iron protein to designate the composition of their redox active metalloclusters. The molybdenum iron protein contains a complex organometallic cofactor which is known as iron molybdenum cofactor and a peak cluster that provides the site for substrate activation and reduction. The molybdenum iron protein contains molybdenum as well as iron sulfur groups, and the iron protein is an iron sulfur protein. The smaller has the molecular weight of 57,000 to 73,000 and contains Fe4S4 cluster. The larger protein has a molecular weight of 2,20,000 to 2,40,000. X-ray studies of Azobacter vinelandii nitrogenase have clarified the presence of two associated proteins in the enzyme nitrogenase, that is molybdenum iron and iron proteins. Molybdenum iron proteins contains a protein P cluster and iron molybdenum cofactor. The major elements of the nitrogenase reactions are iron protein. The iron protein is a homodimer composed of two identical subunits. The two subunits are connected via 4Fe4S cluster. The cluster is ligated with 4 cysteine residues, 2 from each subunit. Molybdenum iron protein P cluster consists of two 4Fe3S clusters linked through an additional sulfide ion, forming the 8th corner of each of the cluster to give rise to a cubane-like structure. These cubane units are further bridged by two cis-thiol ligands, each coordinating one iron from each cluster. The remaining 4 iron atoms are coordinated to 4 additional cis-thiols. Iron molybdenum cofactor, which consists of cuboidal Fe4S3 and Fe3 molybdenum S3 units bridged by 3 sulfide ions. The iron molybdenum cofactor's molybdenum atom is approximately octahedrally coordinated by 3 cofactor sulfide ions, a his imidazole nitrogen and 2 oxygen from a bound homocitrate ion, which is an essential component of iron molybdenum cofactor. The iron molybdenum cofactor contains a central cavity determined by X-ray studies of A. vinelandii. EXAFS analysis confirmed the presence of this core in both the isolated iron molybdenum protein and cofactor. The N2 molecule binding to the active site is still uncertain. At a glance, a trigonal prismatic cavity surrounded by 6 coordinatively unsaturated iron atoms seems to be susceptible to nitrogen insertion, giving rise to mu6N2 ligand. But the cavity size is considered to be too small to accommodate N2. Alternatively, extended Huckel type calculations suggested the coordination of N2 rather to the edge or to the face of F6 trigonal prism as a bridge between two cuboidal units. On the other hand, coordination of cyanide to the isolated iron molybdenum cofactor has been reported to take place at the molybdenum atom from the AXFAS criteria. Albeit this ambiguity of the binding and reduction mechanism of nitrogen In the biological system, it is apparent that the transition metals play an important role in promoting this transformation under mild conditions. Studies of the synthesis and reactions of nitrogen complexes are therefore of particular interest. Mechanism of action. In addition to nitrogen and nitrogenase, nitrogen fixation requires two more participants. First is the source of electrons and second is ATP. Electrons are generated either oxidatively or photosynthetically depending on the organism. These electrons are transferred to ferredoxin, a 4Fe and 4 sulfur containing electron carrier that transfers an electron to iron protein of nitrogenase, beginning the nitrogen fixation process. In vivo, nitrogenase require the delivery of a considerable amount of energy by the act of ATP hydrolysis. This ATP requirement is highly specific and no other nucleotide works. Two molecules of ATP bind to the reduced iron protein and are hydrolyzed as each electron is passed from the iron protein to the molybdenum iron protein. That is, ATP is hydrolyzed as the substrate is reduced. These the precise time at which ATP binds and dissociates and the exact role it plays in the reduction process have not been fully elucidated. During catalysis, electrons flow from the iron protein in the gated process that is controlled by ATP hydrolysis, which leads to accumulation of multiple electrons within the molybdenum iron proteins, which in turn makes iron molybdenum cofactor ready for substrate binding. The sequence of the electron transfer steps in the nitrogenase reaction appears to be. It therefore seems that the role of ATP hydrolysis is to stabilize a conformation in the iron protein that it cannot achieve on its own and facilitates electron transfer from 4 iron 4 sulfur cluster on the iron protein to the P cluster on the molybdenum iron protein. Further, the electrons flow from this P cluster to the iron molybdenum cofactor. Although iron molybdenum cofactor is considered to be a site of nitrogen fixation, exactly how the nitrogen is bound and reduced are largely a matter of speculation. Each of the 6 central iron atoms are linked to only 3 atoms, leaving open a binding opportunity for nitrogen. It seems likely that N2 binds in the central cavity of this cofactor. Theoretical studies suggest that the iron molybdenum cofactors prismatically arranged iron atoms provide favorable interaction sites for N2 and its reduction products. The formation of multiple iron nitrogen interaction in the complex weakens the N-N triple bond and thereby lowers the activation barrier for reduction. Represents the flow of electrons in the nitrogenase catalyzed reduction of nitrogen. The actual reduction of nitrogen occurs on the molybdenum iron protein in 3 discrete steps, each involving an electron pair. In the first step, the molecular nitrogen gets converted into diamine with the release of 2 protons and 2 electrons. Then hydrazine is formed with the release of 2 electrons and 2 protons. Further, ammonia is formed with the release of 2 protons and 2 electrons. Therefore, an electron transfer must occur 6 times per dinitrogen molecule fixed so that a total of 12 ATPs are required to fix one dinitrogen molecule. But for every dinitrogen reduced by nitrogenase, only one hydrogen is produced, an as yet unexplained waste of electrons by the system. Indeed, some organisms incorporate hydrogenase to recycle some of this hydrogen. The stoichiometry of the biological reaction is thus given below. Sensitivity of nitrogenase. Nitrogenase is extremely sensitive to oxygen as it oxidizes iron sulfur cluster. Therefore, nitrogen fixation can proceed only at very low oxygen concentrations. In fact, nitrogen fixation is an anaerobic process. Free-living bacteria that nitrogen fixes cope with this problem in variety of ways, some living only anaerobically or repress nitrogenase synthesis when oxygen is present. Other species solve this problem by the symbiotic relationship, especially between leguminous plants and the nitrogen fixing bacteria. To solve the oxygen toxicity problem, plants produce a protein called ligemoglobin which binds at all the available oxygen and efficiently delivers it to the bacterial electron transfer system. Nitrogen reduction is energetically costly. The total cost of nitrogen reduction is therefore 8 electrons transferred and 16 ATPs hydrolyzed. Hence, nitrogen fixation is an energetically expensive process. Indeed, the nitrogen fixing bacteria in the root nodules of pea plants consume nearly 20% of the ATP that the plant produces. Summary. Nitrogen fixation occurs via two processes, in vitro and in vivo. Nitrogenase is a complex of two proteins that catalyzes the reduction of dinitrogen to ammonia under ambient temperature and pressure. The two proteins are the iron protein and the molybdenum iron protein. The iron protein is a homodimer that contains one 4Fe4S cluster and 2 ATP binding sites. The molybdenum iron protein is a heterotetramer that contains both iron and molybdenum and is the site of nitrogen fixation. Both the components of nitrogenase mediate electron flow to the active center within the complex. The active center of nitrogen reduction is designated as iron molybdenum cofactor. Electrons flow from the reducing agent ferredoxin to iron protein, then to molybdenum iron protein, where substrate reduction occurs. Contrary to previous belief, recent studies indicated that dinitrogen probably does not directly bind to molybdenum. The actual binding site of dinitrogen and mechanism of the reduction of dinitrogen to ammonia is not yet established. In principle, the reduction of nitrogen to ammonia is a 6-electron process. However, the biological reaction always generates at least 1 mole of hydrogen in addition to 2 mole of ammonia for each mole of dinitrogen. Hence, an input of 2 additional electrons is required. In most nitrogen fixing microorganisms, the 8 high potential electrons come from reduced ferredoxins generated by photosynthesis or oxidative processes. 2 molecules of ATPs are hydrolyzed for each electron transferred. Thus, at least 16 molecules of ATPs are hydrolyzed for each molecule of nitrogen reduced. Again, ATP hydrolysis is not required to make nitrogen reduction favorable thermodynamically. Rather, it is essential to reduce the heights of activation barriers along the reaction pathway, thus making the reaction kinetically feasible.